These are the lesson activities for section 4.5 part 2. Okay, we have a 4 by 6 matrix A. So it really helps me to answer these questions to draw a picture of what A must look like. 4 by 6, so 4 rows and 6 columns. Okay, so what is the largest possible value for the rank of A? So the rank is the dimension of the column space, which is the number of pivot columns. So the most pivot columns I could have, right, would be, I'm going to highlight all the places I could have a pivot. First, non-zero entry, right? If I had the maximum number of pivots, that would be 4. Okay, so the largest possible value of rank A would be 4. You could have 4 pivot columns here. The smallest possible value for rank of A would be 0. If you have a matrix full of zeros, it has no pivot columns, so its rank would then be considered 0. Okay, what is the smallest possible value for the dimension of the null space, also known as the nullity of A? Okay, so keep in mind that rank plus nullity has to equal the number of columns in this case, which is 6. Okay, so if I want the smallest possible value of the nullity, I'm going to plug in the largest possible value for rank. And that means the smallest the nullity could be is 2. Okay, sorry about that phone ringing. So the smallest the nullity could be is 2. The largest the nullity could be, that would happen when the rank is the smallest possible. So rank plus nullity has to equal 6. When the rank is the smallest possible, 0, plus what equals 6, that means the largest possible value for the nullity of A is 6. Okay, similar question. This time we have a 6 by 4 matrix. So again, I'm going to draw it. 6 rows, 4 columns. The largest possible value for the rank of A. So that would be pivot columns, right? How many pivots could we have? So I could have a pivot here, 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 and here. There's no other, I only have 4 columns, so I can't create any more pivots. So the largest possible value for rank of A would be 4. The smallest possible value for the rank of A would be 0, in which that's when you have a matrix full of zeros. It's the dimension of the column space is 0 because there are no pivots. The smallest possible value for the dimension of null A. Okay, so I'm going to write out rank A plus nullity A has to equal, in this case, the number of columns is 4. So the smallest possible value for the nullity would happen when the rank is the largest possible, which means the smallest possible value for nullity is 0. And the largest possible value for the nullity happens when the rank is as small as possible. So 0 plus what is 4. So the largest possible value for the dimension of the null space is 4. Okay, consider matrix A, and I've given a row-reduced version of it, and I want to find the rank of A, the dimension of null A, which is the same thing as the nullity, and the rank of A transpose. Okay. So the rank of A, so it's the dimension of the column space, that's the number of pivots. I have 2 pivot columns, which means rank A is 2. The dimension of the null space, also known as nullity A, okay, is the number of free variables. Okay, so my free variable columns would be those 2. So nullity of A is also 2. When I add 2 and 2, I get 4, the total number of columns. Rank of A transpose, that's the same thing as the dimension of row A, which is always the same as the rank of A, the dimension of the column space. Right? Because the way you find a basis for the row space is you take the non-zero columns of the row-reduced matrix. In this case, there are 2 of them. There will always be the same number of non-zero rows as there are pivot columns. So the rank of A transpose and the rank of A are always the same, which means the dimension of the row space is always the same as the dimension of the column space. Okay, express call A, which is the same thing as the row space of A transpose, as the span of a set of linearly independent vectors. Okay, so this is really irrelevant. I'm just going to put it in parentheses. Call A as the span of a set of linearly independent vectors. So call A, express that as the span of a set of vectors that are linearly independent. So that means I'm going to go up to my row-reduced matrix here. I identified the pivot columns by looking at the row-reduced matrix, but I'm going to take the pivot columns from A itself. That's a linearly independent spanning set, also known as a basis. Okay, C, express null A as the span of a set of linearly independent vectors. So here you have to imagine that you have solved AX equals 0, right? Because that's the null space. That's how you find the null space. Null A is solutions to AX equals 0. And the way you solve that is you would augment with zeros, which wouldn't change over here. They'd also be zeros. All right, and then I'm going to write out the solutions. So I'm going to do it right. I'm going to do it up here so I don't have to scroll down. Okay, so this says x1 plus 2x2 plus 3x3 equals 0. And it says x4 equals 0. All right, I'm going to put that solution set, I'm going to solve it for the basic variables or the pivot variables in terms of the free variables. Okay, so I get x1 equals negative 2x2 minus 3x3, and x4 equals 0. Then I'm going to write it in parametric vector form. So these x's that I'm looking for, they look like x1, x2, x3, x4. And I got to set up a vector for each free variable. Okay, x1 is negative 2x2 minus 3x3. x2 is free, so I'm going to put a 1 and a 0. x3 is free, 0 and a 1. And x4 is 0, so 0 and 0. Okay, so now this is the same thing as the span of those two vectors. Just a different way of writing the solution set. Because the span is the set of all linear combinations, and that's exactly what you've written here, what we've written here. I have some weights that I've put on the vectors and I'm adding them together. The weights can be anything, so this is the set of all linear combinations of those two vectors. Okay, now I want to express rho A as the span of a linearly independent set of vectors. So the way you get rho A, a basis for rho A, is you take the non-zero rows of the row-reduced matrix. So the first row and the second row. And this differs from finding a basis for col A in that here I'm going to use the actual rows from the row-reduced matrix. I'm not just identifying which rows to take from the original, which is what I do for col A. For row A, use those highlighted rows. So I'm going to have 1, 2, 3, 0, and 0, 0, 0, 1. So row A is the span of 1, 2, 3, 0, and 0, 0, 0, 1. The non-zero rows of the row-reduced version of matrix A. Okay, similar kind of problem. I've got a matrix A and its row reduction, and I want to give the rank of A, the nullity of A, and the rank of A transpose, which is the same thing as the dimension of the row space. So rank A is the number of pivot columns in A. I can find pivot columns by looking at the row-reduced matrix. There are 2 of them. Okay, the dimension of the null space, also known as the nullity of A, would have to be 1 because there is 1 free variable and there's 1 column left in A. And the rank of A and the nullity of A have to add up to the number of columns. Okay, and then the rank of A transpose, which is the same thing as saying the dimension of the row space of A. That's always the same as the rank of A, 2. The number of non-zero rows in the row-reduced matrix. Okay, express col A as the span of a linearly independent set of vectors. So that would be the pivot columns of the original matrix A. So that would be 1, 0, 2, and -1, 1, -2. And then I want to do this, find a linearly independent spanning set or a basis of null A. I have to write out the solutions to AX equals 0. So imagine augmenting this with 0, 0, 0. Write out what these things say. This says x1 is 0, x2 plus 2x3 is 0. And then I'm going to translate that to parametric vector form. First, I have to solve for the pivot variables or the basic variables. So I already have x1 equals 0 and x2 equals -2 x3. So null A is the set of all x's that are solutions to this equation I need a variable, a vector for each free variable. My free variable is x3. It's the only one. x1 is 0. x2 is -2 x3. And x3 is free. So null A is the span of 0, -2, 1. Okay, finally, I want to express rho A as the span of a linearly independent set of vectors. Those are the non-zero rows of the row-reduced matrix, 1, 0, 0, and 0, 1, 2.